2.5, zeros of a polynomial function. So our objectives for this section are to use the rational zero theorem to find the possible rational zeros, to find the actual zeros of a polynomial function, to solve any sort of polynomial equation, and then to use the linear factorization theorem to find polynomials with given zeros. And then finally to use something called Descartes' rule of signs. So in the last section, we used polynomial long division to try to figure out if a polynomial is divisible by some sort of factor. Okay? In this section, we are actually going to find all the factors of a polynomial, so that way we can solve polynomial equations. And we're going to do this primarily using not long division, mostly synthetic division, because it's faster. So when finding zeros of a polynomial function, what kind of numbers can you get? Well, we could have rational zeros like -3 and 1/2, which comes from factors that look like that. We can have irrational zeros like negative radical 2 and positive radical 2, which come from factors that look like that. And we could have complex zeros, imaginary zeros, which come from factors that look like that, a little more complicated. And notice that when we have irrational zeros or complex zeros, right, they always come in conjugate pairs. So we have negative radical 2, positive radical 2. We have 4 minus 5i, 4 plus 5i. That's going to be very important when we start to talk about those types of zeros later. But we can have real zeros, we can have non-real zeros, any types of zeros. And when I multiply all of these factors together, then I will get my original polynomial function. Okay? So to help us get all those zeros, because we're not necessarily going to be given any of them, in order to get all these things, we're going to use something called the rational zero theorem. The rational zero theorem provides us a tool that we can use to make a list of all possible rational zeros, not the actual zeros, right? All the ones that are actually possible. Equivalently, the theorem gives us all possible rational roots of a polynomial equation. Not every number in the list will be a zero of the function, but every rational zero of the polynomial function will appear somewhere in that list. Okay, so that's all the rational zeros. So polynomials can have other types of zeros, right? We can have irrational zeros and imaginary zeros, but if we focus on the rational zeros first, this will give us a good path to find all the zeros, and we'll see how that works a little bit later. But first, the rational zero theorem works pretty simply. It works like this. If we have a polynomial function, f of x is equal to our standard polynomial function, and it has integer coefficients, and p over q, where p over q is reduced to lowest terms, is a rational zero of the function. Then p is a factor of the constant term a sub 0, that thing. Q is a factor of the leading coefficient, a sub n, that thing. So that means that if we have a polynomial function with integer coefficients, we can take the factor of the constant term, divide it by a factor of the leading coefficient, and that will be a possible rational zero in the polynomial function. So my possible rational zeros are going to be the factors of the constant term divided by the factors of the leading coefficient. Let's see how this works. Okay. So our example 1, using the rational zero theorem, list all the possible rational zeros of this polynomial function. So first, I look at this term right here. So we can say the factors of a sub 0, which is the constant term, which is 4, are, well, what are all the numbers that multiply together to give you 4? Well, 1 times 4 and 2 times 2. But couldn't I have -1 times -4 also give me a +4? Sure. So we can say it's plus or minus 1, plus or minus 2, and plus or minus 4. Okay? We are always, when we're thinking of rational zeros, going to think about positive and negative numbers. So there are 6 possible factors of the constant term. Okay, next, the factors of a sub n, the leading coefficient, okay, which is -1, as you can see right there. Okay, so the factors of -1 are very easy, plus or minus 1. Okay, so from the last page, the possible rational zeros are the factors of the constant term divided by the factors of the leading coefficient. So we have to take all of these numbers right here and divide them by everything down there. So that's going to be plus or minus 1, plus or minus 2, plus or minus 4, all divided by plus or minus 1. Okay, which in this case is going to be pretty simple because, right, if we take everything divided by a +1, we get the same thing. If we take all these divided by a -1, we just get the opposite. Okay, and we're always going to have positive or negative terms. So my possible rational zeros become plus or minus 1, plus or minus 2, plus or minus 4. Okay, and we can write them with the plus or minus instead of having to list each one. 1, -1, 2, -2, 3, 4, -4. Okay, factors of that divided by the factors of that. Let's look at a checkpoint problem. Okay, list all the possible rational zeros of this polynomial function. So we take the factors of 6 divided by the factors of 1. And I don't really need to worry about signs too much when I'm talking about rational zeros because they're always all going to be positive or negative. Okay, so basically, because there's a 1 in the front here, this becomes pretty easy, and I just look at all the possible rational zeros of 6. Well, all the factors of 6 are 1 and 6, 2 and 3. So my possible rational zeros became plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. All of those divided by 1, which is the same number. All these divided by -1, which just turns into the opposite. And those are just going to be all my factors. Okay. So it's a little easier when we have a situation like this with a +1 or a -1 in the front. It becomes a little more complicated when there is something like a 15 in the front here. Okay, so remember what we're going to do. We're going to take all the possible rational zeros are going to be the factors of the constant term divided by the factors of the leading coefficient. Okay, well, let's list all the factors of the constant term. That's 1 and 2. All the factors of the leading coefficient is 1 and 15, 3 and 5. Okay, so my rational zeros, my possible rational zeros are plus or minus 1, plus or minus, plus or minus 2, divided by plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. Okay? All of those are going to be my possible rational zeros. Okay? So let's do both of these divided by 1, divided by 3, divided by 5, divided by 15. Well, plus or minus 1, when I divide those both by 1, I get plus or minus 1, plus or minus 2. Okay, let's divide these both by 3. So that's plus or minus 1 over 3, plus or minus 2 over 3. Okay, so in the denominator here is my first factor of the leading coefficient, which is 1. Here's the second factor, which is 3. Now I'm going to take both of these terms and divide them by 5. So that's 1/5 and plus or minus 2/5. And then finally, both of them divided by 15, plus or minus 1 over 15, plus or minus 2 over 15. Ran out of space there. But you can see that we have these two terms occur over 1, over 3, over 5, over 15, over all the factors of 15. So it's the constant term divided by the factors of the leading coefficient. Let's look at another one. So my factors of 3 are 1 and 3. My factors of 4 are 1 and 4, 2 and 2. So I want all the factors of 3 divided by, so this is going to be plus or minus 1, plus or minus 3, divided by plus or minus 1, plus or minus 2, plus or minus 4. Okay, so my answer becomes plus or minus 1, plus or minus 3, both of these divided by 1, plus or minus 1/2, plus or minus 3 over 2, both of these divided by 2, and plus or minus 1/4, plus or minus 3/4, both of these divided by 4. Okay, so all of the coefficients of the lead term divided by, or sorry, all the coefficients of the constant term, all the factors of the constant term divided by all the factors of the leading coefficient. Now, why do we care? Why do we care what the possible rational zeros are? Well, if I look at this function right here, I don't know how to factor something x to the 5th power. Okay, and it's missing a couple of degrees in there. There's no technique that I can use to factor this. I can't use grouping. I can't use anything crazy. Okay, so what I'm going to have to do is somehow, actually I could use grouping on this, but whatever, is I'm going to somehow have to guess about what zeros could actually work, which one of these could actually be a factor. And then I'm going to factor that out. I'm going to divide it out. And I'm going to be left with something a little simpler. And then I'm going to use any techniques that I can. Okay? So how do we determine which, if any, possible rational zeros are the actual rational zeros of a polynomial function? To find the first rational zeros, we use trial and error. You try one, you see if it works. If it does, great. If it doesn't, you try a different one. With synthetic division. Okay. If f of x is divided by x minus c and the remainder is 0, then c is a 0 of the function. So that's what we're looking for. We're looking for one of these zeros to, when you use synthetic division, to give you a remainder of 0 to actually work. After we identify the first rational zero, we use the result of the synthetic division to factor the original polynomial. Then we set it equal to 0 and do whatever we need to do with it. Okay? So let's look at this one. This is a x to the 3rd problem. Okay? The only technique I have to factor x to the 3rd is to notice first if it's a difference or sum or difference of cubes, which it's not, or to factor with grouping, which I can't. So my only option now is to try to guess something to factor out. Well, I could guess anything, but if I use the rational zero theorem that we just learned, I could guess one of the possible rational zeros. So my possible rational zeros are going to be the factors of 6 divided by the factors of 1. So that's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So one of those 8 factors, right? Positive is 1, negative is 1. One of those 8 factors should work, okay? Unless this thing has no possible rational zeros, which is not possible because, actually it is possible, but we know it's going to have at least one real zero because both sides go in opposite directions, and it's not possible to go for both sides to go in opposite directions and not cross the x-axis somewhere. So every function that has an odd degree, and we'll talk about a little bit more about this in the next section, but every function that has an odd degree has to cross the x-axis at least once. Okay, so I'm going to guess a 0 that might work. And I'm going to start at the most logical place with 1. So I'm going to start with 1. I'm going to use synthetic division, which hopefully you remember we strip only the coefficients. So that's 1, 2, minus 5, minus 6. And let's see if this works. Bring down the 1, multiply, add, multiply, add, multiply, add. That is my remainder. It's not a 0. 1 is not a 0 of this polynomial. Okay, I don't get discouraged. I next try -1. So that's 1, 2, minus 5, minus 6. And bring down the 1, multiply, add, multiply, add. And when I multiply, I get that this is a 0 of the polynomial function, that -1 is a 0. Okay, that's great. This now is my reduced polynomial. Okay, so remember what this means. When we're factoring out, this is the factor. Okay, so we factored out x minus x plus 1, right, because we changed the sign there, right, because now x is equal to -1. And if I want the factor, I set it equal to 0, so x plus 1 would equal 0. That's my factor. This is the polynomial that's left over. Remember to reduce the degree by one degree. So this is now x squared plus x minus 6. And now I can continue factoring this without resorting to guessing rational zeros. I can just use my quadratic techniques. And I should see the factors of 6 that subtract to 1 are x minus 3, x plus 3, x minus 2. Okay. Now I have successfully factored this. And notice that these two factors are in my list of rational zeros. Okay. And if I wanted to solve this, I could, of course, set it equal to 0 and solve it for x is equal to -1 here, x is equal to -3 there, and x is equal to 2 there. So my solution set becomes x is equal to the set of -3, -1, and 2. And those are the 3 zeros of my polynomial function. Let's look at this problem, this next one. Find all the zeros of this polynomial function. So I'm going to start with plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. Okay, well I could start at some of the bigger numbers up there, which is, this is all the factors of 20 divided by 1. But let's start with the easy one. Start with 1. It's a good place to start. Okay, 1, 8, 11, -20. Bring down the 1, multiply, add, multiply, add, multiply, add, and look at that. Isn't that nice? Okay, so my first factor becomes x minus 1. My second factor, remember, this is x. So if x is equal to 1, the factor, when I set that equal to 0, is x minus 1. And we have x squared plus 9x plus 20. Continue factoring. And we have x plus 4, x plus 5. And notice that both of those are in my list of rational zeros. So x would equal to -5, -4, and 1. Okay. Very good. So our work in the last couple problems involved finding zeros of a third degree polynomial function. The rational zero theorem is a tool that allows us to rewrite such functions as the product of two factors, one linear and one quadratic. Then the zeros of the quadratic factor are found by factoring, which is how we could do this problem and the problem after it, or if it doesn't factor, by using the quadratic formula. Okay, so let's try one where the answer might not factor. Okay, so again, we have a cubic function, we have a cubic polynomial function. My possible zeros, rational zeros, are plus or minus 1, plus or minus 3. Okay, so those are the zeros that I'm going to test first. Okay, and of course, I'm going to start at 1. Of course, don't forget, check that. For any missing zeros, there's none. So we got 1, 7, 11, negative 3. Synthetic division, 8, 19, and not 0. No good. Let's try negative 1. 1, 7, 11, negative 3. Bring down the 1. Multiply. Add, we get 6. Multiply, get negative 6. Add, we get 5. Multiply, we get negative 5. And add, we get negative 8. No good. Squeeze in 3 right over here. We got 1, 7, 11, negative 3. Bring down the 1. Multiply. Add together 10. Multiply. Add together 41. And of course, I don't even have to finish this because I could tell that it was going to be way too big. Okay, well, we got one more chance. So let's try negative 3. Okay, that's 1, 7, 11, negative 3. Bring down the 1. Multiply. Add them together, 4. Multiply, that's negative 12. Add them together, that's negative 1. Multiply together, we get a 3. And look at that. There is my new polynomial function. Okay, so my first factor that works was x plus 3. My second left over is x squared plus 4x minus 1. But there's a problem here. There are no factors of 1 that subtract to give me 4. Okay, so because this doesn't factor, we must now resort to the quadratic formula. Negative b plus or minus b squared minus 4ac all over 2a. Okay, so x is going to be equal to negative 4 plus or minus the square root of 4 squared minus 4 times 1 times negative 1 all over 2 times 1. Okay, so that gives me negative 4 plus or minus the square root of 16. Negative and negative turn positive, so that's going to be 16 plus 8, or plus 4, which is going to give me 20. So that's over 2. The square root of 20 I can simplify, so that's negative 4 plus or minus, turns into 4 times 5, so that's 2 square root 5 over 2. And of course, I can reduce to give me negative 2 plus or minus the square root of 5. Okay. So, I now have my 3 answers. 1, so x is going to be equal to, the first answer was negative 3, because that's the one that worked. Okay, and then my next 2 answers are negative 2 minus the square root of 5 and negative 2 plus the square root of 5. And those are the three zeros of this polynomial function. One of them is rational, two of them are irrational, which is fine. Still numbers and still valid answers. Let's try another one just like that, okay? So my possible rational zeros become plus or minus 1, plus or minus 2. Those are the ones that I'm going to check. Let's try one first. 1, 1, negative 5, negative 2. Bring down the 1. That's 2. Negative 3. No good. Let's try negative 1. 1, 1, negative 5, negative 2. Bring down the 1, negative 1, 0, 0, minus 5, 5. That's going to be 3. No good. Let's try 2. And you just keep trying these, okay? I know that one of these is going to work, so we just keep trying them until they do. So we got 1, 1, negative 5, negative 2. Bring down the 1, 2. That's a 3. That's a 6. That becomes a positive 1, which turns into a positive 2. And there's my first factor. So we have x minus 2 times x squared plus 3x plus 1. Unfortunately, I cannot factor that, which means I have to use the quadratic formula. So a is going to be 1, b is going to be 3, c is going to be 1. So x is going to be equal to negative 3 plus or minus the square root of b squared, that's 9, minus 4 times 1, minus 4, over 2 times 1 is 2. So we have negative 3 plus or minus the square root of 5 over 2. That does not simplify anymore, so my answers become x is equal to my rational 0, negative 3 plus the square root of 5 over 2, and negative 3 minus the square root of 5 over 2. My one rational 0 and my two irrational zeros. If the degree of a polynomial equation is 4 or higher, it's often necessary to find more than one linear factor by synthetic division. You can speed this up if you happen to have access to a graphing utility. So when I look at this function right here, I could realize that the possible rational zeros are going to be all the factors of 24 divided by all the factors of 1. So that is going to give me plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and plus or minus 24. Right? 1 times 24 is 24, 2 times 12, 3 times 8, 4 times 6. That's 1, 2, 3, 4, 5, 6, 7, 8. That's 16 different factors to try to check. Kind of a lot. Okay? If we had access to a graph, we could maybe look at the graph, and it tells me something very important. That this graph happens to touch the x-axis at 2, which means that 2 is a 0 of the polynomial function. So what I'm going to do is I'm going to use synthetic division with 2. 1, negative 6, negative 8, 24. If you did this, you would actually be wrong. Be careful right here because we're missing an x to the third power. It means we have to include a 0. Okay, so x to the fourth, x to the third, x squared, x, and my constant. Bring down the 1. Multiply. Add these together. Multiply. Add these together. Multiply. Add these together. Multiply. And it works. And it should have worked because I can clearly see that 2 is a 0 of the polynomial. Now, this is still x to the third plus 2x squared minus 2x minus 12, which I can't really factor very well the way it is. So I'm going to have to keep guessing and checking to see what other factors work. But if I remember last lesson, to my multiplicities, because the graph touches the x-axis and goes the other direction, this particular 0, 2, has a multiplicity of 2, which means it happens twice, which means I can divide it out again. And I can do that by continuing to divide the polynomial. I want to divide this result polynomial because if I divide the original equation, I will get a different polynomial that is still x to the third power. I want to divide x to the fourth power and turn it into x to the third, which I did, and now I want to turn x to the third into x squared. Once you get the polynomial down to an x squared, down to a quadratic, you can now factor it with quadratic techniques. Break down the 1, multiply, add 8, multiply positive 6, and we get x squared plus 4x plus 6. Unfortunately, from there, right, the factors of 6 that add to 4, well, it's not 1 and 6, it's not 2 and 3, so that means we're back to the quadratic formula. Let me put it down here a little bit so I have some more room. X is going to be equal to negative b plus or minus the square root of b squared minus 4 times 1 times 6 all over 2. Now, when I try to work this, clearly you can see that underneath the radical is going to give me a negative 8. Okay? And remember, the first thing we do with the negative underneath the radical is bring it to the outside by turning it to an I. So it's plus or minus I square root 8 over 2, which I can simplify to negative 4 plus or minus 2I radical 2 over 2, which the 2's cancel, and we get negative 2 plus or minus I radical 2. So I have, from my fourth degree polynomial, I have 4 answers. They are 2, which happens twice, 2 with a multiplicity of 2, negative 2 plus I radical 2, and negative 2 minus I radical 2. So this answer happens twice, and I'll have to write it twice. And my other 2 answers are imaginary, which kind of makes sense when I look at this graph, is that this graph does not touch the x-axis anywhere else. So these are the only 2 real zeros it has. It does have a little inflection point over here, okay, which means we're going to have some more zeros somewhere, but they happen to be imaginary, which means they don't cross the x-axis. Okay. And also notice that they are conjugates of each other, and we'll talk about that in another second. Let's do another one of these problems. Okay. So, I do have the picture of the graph over to the right, but I don't want to use it. I want to try this. Let's pretend that you didn't have the picture of the graph over there. And let's do this just with a guess and check technique. Okay, so my possible rational zeros are plus or minus 1, plus or minus 13. So not as many, so this one's actually a little bit easier. All right, let's start with 1. So that's x to the fourth, x to the third, 22, minus 30, and 13. bring down the 1, multiply, add this, you get a positive 17, multiply, add, and look at that. Okay, so 1 happened to be a root. That's great. Okay, but we can't just move on to another root. Okay, we should check 1 again to see if it happens to be a multiple root. Okay, so you can, if 1 hadn't worked, we could automatically throw it out. It's never going to work. But since 1 worked the first time, it could work again. And we keep trying the same 0 over and over again until we get it to stop working. Or until we get down to a quadratic. And we only need 1 more. So I'll bring this down. 1, multiply, add, multiply, add those together. We get a positive 13. And look at that. So my resultant function that's left is x squared minus 4x plus 13. Unfortunately, the only factors of 13 are 1 and 13, and they do not add up to 4. So that means to find the last 2 factors, I'm going to have to use the quadratic formula. So that turns into, remember that a is 1, b is negative 4, and that c is 13. So we have negative b, that's a positive 4, plus or minus the square root of 16 minus 4 times a times c, which is going to be 52 over 2. 16 minus 52 gives me a x is equal to 4 plus or minus the square root of negative 36 over 2. Well, that works out very nicely to give me 4 plus or minus 6i over 2, which is 2 plus or minus 3i. Okay, so this function has 4 zeros, 2 of which are imaginary, and they are 1 twice, 1 with a multiplicity of 2, 2 plus 3i, and 2 minus 3i. Okay, not a parenthesis. Okay, so my zeros, 2 real zeros, 2 imaginary zeros, means that if I were to actually look at this graph, what I would expect to happen is for the graph to touch at 1 and to turn the other direction and then to never cross the x-axis again. And that is kind of what we have going on right here. Okay? And this graph does have another turn as you go further up, but I just didn't include it in the picture. Okay, so some important properties of the roots of polynomial equations is that, number 1, if a polynomial equation is of degree n, then counting multiple roots separately, the equation has n roots. If a plus bi is a root of a polynomial, then the imaginary number a minus bi is also a root. Imaginary roots, if they exist, occur in conjugate pairs, always. Okay, and that is something called the fundamental theorem of algebra. So the fact that polynomial equation of degree n has n roots is a consequence of a theorem proved in 1799 by a 22-year-old math student named Carl Friedrich Gauss in his college doctoral dissertation. His result is called the fundamental theorem of algebra. So basically, the fundamental theorem of algebra says that if you have a polynomial of degree n, where n is bigger than 1, and the equation f of x has at least one complex root. So that means for every polynomial, you're going to get at least one complex root. Suppose, for example, that f of x equals 0 represents a polynomial equation of degree n. By the fundamental theorem of algebra, we know this equation has at least one complex root. Call it C1. By the factor theorem, we know that x minus C1 is a factor. Therefore, we can take this factor, multiply by the quotient, and it's going to be equal to 0. Okay, that means that x minus c is equal to 0, or the quotient times x is equal to 0. If the degree of q1 of x is at least 1, the fundamental theorem of algebra says that it has at least one complex 0, and we call it C2. And hopefully you can kind of see where this is going. You can factor it out, you can split it into two factors, and you can keep going. Okay? When we continue this process, right, you have that f of x is equal to 0, you factored out the first one, you factored out the second one. When you continue this process, you obtain the product of n linear factors. Setting each one of these little linear factors equal to 0 gives you n complex roots. Therefore, if f of x is a polynomial of degree n, where n is bigger than 1, the function, the polynomial, has exactly n roots, where the roots are counted according to their multiplicities. So that means if we have a fourth degree polynomial, like in example 5, right? We found that this polynomial had 4 roots, 2 twice, and then 2 imaginary, right? Where 2 is a repeated root with multiplicity 2. The polynomial can be factored over complex non-real numbers as follows, by splitting it into the 4 factors. X minus this factor, x minus this factor, x minus 2, x minus 2. These are my 4 linear factors. Okay, this fourth degree polynomial has 4 linear factors, just as an nth degree polynomial has n roots. An nth degree polynomial has n linear factors. This formally stated as the linear factorization theorem. So here's the formal definition for the linear factorization theorem. It says that we can break a polynomial function into a bunch of linear factors multiplied by itself and possibly a coefficient in the front. So basically, let's backtrack a little bit. The fundamental theorem of algebra says we have a fourth degree polynomial, you're going to get 4 answers. Some real, some imaginary, some maybe more than once. The linear factorization theorem says that we can take those roots and write linear factors for them. So if x is going to be equal to 2, x minus 2 is my factor, right? I change it from a root to a factor by setting it equal to 0. The only time this gets a little more complicated, like with these 2 factors, is if x is equal to, let's say, 2 plus 3i, if we set that equal to 0, I would say my factor that generated this root is x minus 2 minus 3i. Okay? Because I would move both of these to the other side. Okay? And of course, if this is a factor, if this is a root, this must also be a root, which means that another root would be x minus 2 plus 3i when I set that equal to 0. So remember that imaginary complex numbers always come in conjugate pairs, as well as irrational numbers as well. So any radicals or any imaginary are always going to come in conjugate pairs. So many of our problems involving polynomial functions and polynomial equations have dealt with the process of finding the zeros and the roots. The linear factorization theorem enables us to reverse this process and find the polynomial. So with this function, I have a fourth degree polynomial with real coefficients that has -2, +2, and I as a 0. Well, if it's a fourth degree polynomial, it has to have 4 roots. I only see 3 there. But I know that if I have I as a 0, I also must have its conjugate, -I. So x is going to be equal to -2, +2, I, and -I. Okay, and then we have that f of 3 is equal to -150. Okay, so this is going to help us get our coefficient in the front. Okay? These zeros are going to help develop my polynomial. Let's try it. So we can say that f of x is going to be equal to some coefficient times my 4 factors. So my first factor is going to be x plus 2. My second is x minus 2 from these two. Next is x plus I and x minus I. Doesn't really matter what order you write them in. Okay? And in fact, it's probably easiest to multiply the conjugate pairs together first, because since they're the difference of squares, it turns into x squared minus 4, and then this turns into x squared plus 1, the sum of squares, right? Because I times -I is -I squared, which turns into +1. Okay, so let's keep this going and let's simplify this one more time. So a sub n is going to equal to these two FOILed together, which is going to be x to the 4th minus 3x squared minus 4. Okay, so there's my polynomial function, but I'm missing that lead term right there. But luckily, I have this last piece of information right there, that f of 3 is equal to -150, which means that f of 3 of this polynomial function, let's actually write it out. Let's plug in 3. 3 to the 4th power minus 3 times 3 squared minus 4 is going to be equal to -150. Okay? So I only have one variable now. I can solve this pretty easily. So we got a sub n is equal to 81 minus 27 minus 4, which is 50. So that's 50. A sub n is equal to -150. Divide out the 50, so a sub n is going to be equal to -3. Which means that my polynomial function becomes -3 times x to the 4th minus 3x squared minus 4. But that's not in standard form yet. I actually have to distribute the -3. So we get that my polynomial function, that f of x is going to be equal to -3x to the 4th plus 9x squared plus 12. And there's a polynomial function that has 4 zeros, -2, +2, -I, +I, and where f of 3 is equal to 150. Okay? Let's try that again. Find a, whoops, find a third degree polynomial that has -3, I, also -I, and that f of 1 is equal to 8. Okay? So we know my function is going to equal to some coefficient times x plus 3, x plus I, x minus I. Let's multiply the conjugate pair together because that's a little bit easier, because that's x squared plus 1. FOIL this out, and we get x to the 3rd, x times x to the 3rd. Let's just put it in standard form right off the bat so I don't have to rearrange anything. So that's 3x squared plus x plus 3. There's my polynomial function, but I'm missing that term. Luckily, I know that f of 1 is equal to 8. So I can say that 8 is going to be equal to a sub n, plug in 1 for everything, 1 to the third, plus 3 times 1 squared, plus 1, plus 3. So 8 is going to be equal to a sub n times 1 plus 3 plus 1 plus 3, which is 8. So 8 is equal to 8a sub n. So a sub n is equal to 1, which means that my polynomial function is simply the answer that I got previously. So f of x, right, if I just plug a 1 in there and multiply it out, I'm going to get the same thing. X to the third plus 3x squared plus x plus 3. And there's my polynomial function. Okay. Descartes' rule of signs. Because an nth degree polynomial equation might have roots that are imaginary, we should note that such an equation can have at most n real roots. So Descartes' rule of signs provides even more specific information about the number of real zeros in a polynomial. The rule is based on considering variations in sign between consecutive coefficients. For example, this polynomial right here has 3 sign changes. It starts positive, changes to negative, stays negative, changes to positive, stays positive, changes to negative. So we look from left to right and we just say, that's a change, that's a change, that's a change. So this particular polynomial has 3 sign changes. And the number of sign changes can help us figure out what's going on with zeros. So start with your polynomial with real coefficients. The number of positive real zeros is the same as the number of sign changes of the function, or less than the number of sign changes by a positive even integer. So that means in this particular function, there are 3 sign changes. So that means there are 3 positive real zeros, or we go down by 2. There could be 1. Okay, so Descartes' rule of signs is not specific. It doesn't tell you how many zeros there are, how many positive real zeros there are, or how many negative real zeros there are. All it tells you is how many there could be. And it always goes down by 2, because if you have 1 imaginary zero, you must have 2. You must have the conjugate. Okay, so we're always going to count the number of sign changes, take that number, and go down by 2's until we get to 0 or 1. That's positive real zeros. For negative real zeros, we have to look at f of negative x. So we must change the sign of any, we plug in negative x, which means that we change the sign of any coefficient that is attached to a odd degree exponent. And same thing, we count the number of sign changes in my new function, and then we go down by 2's. We go down by a positive even integer. Okay? So, here is a function. There are 1, 2, 3 sign changes, which means there's 3 positive real zeros, or 1 real zero. So there's 3 or 1. Okay? Here is another function, like, see, positive, positive, no sign change. To negative, that's 1. To positive, that's 2. Stays positive. So that's 2 sign changes. So there are 2 or 0 positive real zeros. In this function, negative, negative, positive, positive, there's only 1 sign change, so there's only 1 real zero. There's only 1 positive real zero. Okay? So looking at the number of sign changes tells us how many possible positive real zeros there could be in this function. So it doesn't mean there's 3, and it doesn't mean there's 1. There's 1 or the other. Okay? So with a 7th degree polynomial, there has to be at least 1 zero that crosses the x-axis, and in this case, it must be positive. In this case, with a fifth degree polynomial, I know it has to cross the x-axis, uh, although the place where it crosses the x-axis does not have to be positive, because there could be 2 or there could be 0 positive real zeros, which means that it must have at least 1 negative real zero. So let's see how this actually works. And let's use Descartes' rule sign to see the number of sign changes. Positive, 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 positive. There are no sign changes for this function, okay? So there are no positive real zeros, okay? But now we have to look at this function, f of negative x, okay? So in order to find out my negative real zeros, I need to replace x with negative x and count the sign changes. So that means I'm going to go negative x to the third plus 2 times negative x squared plus 5 times negative x plus 4. This becomes negative to the third power changes to a negative. Negative squared turns positive. 5 times negative x is a minus 5x plus 4. And notice that the only two things that changed were the terms that have odd exponents. Count the sign changes. 1, 2, 3. 3 sign changes. That means that there are 3 or 1 negative real zero for this polynomial function. Okay. So what does this mean for us? Okay. If we wanted to solve this, okay, the possible rational zeros, if I look at this function, right, and there's a 1 in the front there, are plus or minus 1, plus or minus 2, or plus or minus 4. But I just found out that there are no real zeros, no positive real zeros. So that means that the positives here won't work. That means if I'm going to start testing numbers, the best place to start is at 1 or negative 1. Okay. So if I wanted to actually solve this, my first guess would be a negative 1. Okay, let me see my function again. And that would be 1, 2, 5, 4. Bring down the negative 1, or bring down the 1. Multiply, add, multiply, add, multiply, and look, I get that to work very nicely, which gives me a resultant equation, x squared plus x plus 4, which does not factor, so I would have to use the quadratic formula. Okay, but I have one positive real root. Okay, I am not going to get real roots out of this, because if I did, I would have a conjugate, which means that I would get a positive real root somewhere. Okay, so I'm probably going to get 2 imaginary roots out of this, which is fine. Descartes' rule of signs doesn't say anything about the number of imaginary real roots. All it says is about the positive and negative real zeros. Okay. Look at the number of sign changes. 1, 2, 3, 4. So that is 4, 2, or 0 positive real roots. And then what I like to do as a little shortcut is that sign's going to, as if when I plug in negative x, I know that everything with an even exponent is going to stay the same. Everything with an odd exponent is going to change signs. So I just like to give myself a little notation that for f of negative x, that's going to be positive, that's going to be positive, that's going to stay positive, that's going to turn positive, that's going to stay positive. So there are no negative real roots. Okay? Because there's no sign changes. Okay? So Descartes' rule of signs can help us eliminate some of the possible rational roots but it doesn't really give us any answers to help us solve this faster. Finally, kind of a harder problem. So, what's happening in this problem is that we're given a polynomial and we're given a root. And if 2 minus 3i is a 0 of p, 2 plus 3i must also be a 0 of p. Okay. So now I have two roots. And if I could divide both of these out, then I would have an x squared. Then I would be able to solve this polynomial equation. So in order to do this, I'm going to have to use synthetic division with an imaginary number. Let's see how that works. 2 minus 3i is my first root. That's given to me. I know it's going to work. 1, negative 6, 20, minus 22, and a minus 13. And we're given a lot of space here because it's going to get fairly complicated. Bring down the 1. Okay? And the first, when we're dividing, when we're using synthetic division with imaginary numbers, the first division is going to be kind of complex. The second division should be kind of easier if you did it correctly. Okay, so bring down the 1 and you multiply. So that turns into 2 minus 3i. Now remember, when you add real and imaginary numbers, only the real parts combine. So this turns into negative 4 minus 3i. However, now we must multiply 2 minus 3i times negative 4 minus 3i. Remembering, of course, to FOIL those two polynomials together. Okay, so this gives me negative 8 minus 6i plus 12i plus 9i squared, which turns into minus 9, which gives me a negative 17 plus 6i, which goes here, minus 17 plus 6i. Okay? Add the real parts together, and we get 3 plus 6i. And then guess what? Now we must multiply these two together again. 2 minus 3i times 3 plus 6i. And I'm just going to do this on my calculator. 2 minus 3i times 3 plus 6i gives me 24 plus 3i. Add these together, we get 2 plus 3i. Ooh, now look, we have two conjugates, 2 minus 3i times 2 plus 3i. That's good because when you multiply two conjugates together, you get a real number. Okay, so when I multiply these two together, I'm going to get a positive 13, which is good that it worked out because it's a given to me that it's a 0, so it should work out. Okay, that was step 1. Okay. Next, we're going to divide out the next imaginary number, 2 plus 3i. Okay. Now this one is a little bit easier because watch what happens. Okay, bring down the 1. Multiply 2 minus 3, 2 plus 3i. Sorry. I's cancel, and we're left with a negative 2. Multiply both of these. We get negative 2 times 2, that's negative 4, minus 6i. The i's cancel, and we're left with negative 1. Multiply both of these, and we get negative 2 minus 3i. Which works, which is good, because it's supposed to. Okay, so the first division is rather difficult. The second division should work out very nicely. If it doesn't, you better check you did something wrong. Okay, started this polynomial with x to the fourth, dividing out a linear factor. This is still a linear factor, turns it into x to the third in this row, x squared right here. So we're left with x squared minus 2x minus 1, which very conveniently factors into, no, actually, take that back. That's 1 and 1, but the signs aren't going to match. So this does not factor. So we now must use the quadratic equation. So my other x's are going to be b, negative b, plus or minus the square root of b squared minus 4 times a times c. So that's 4 times negative 1 times positive 1. So that's going to be a positive 4 over 2. So we're going to get 2 plus or minus 2 radical 2 over 2. So that's going to be 1 plus or minus radical 2. So this particular equation, now, if we're going to break it down into our factors, has 4 factors, or has 4 answers. X is going to be equal to 2 minus 3i, 2 plus 3i, comma, 1 plus radical 2, 1 minus radical 2. Okay? If I want to break this into its linear factorization, I'm going to have to take all these factors and make, or all these zeros and make factors out of them. Remember, these are all x is equal to 2 minus 3i. For factors, I set them equal to 0. So it turns into x minus 2 plus 3i, x minus 2 minus 3i, x minus 1 minus radical 2, and x minus 1 plus radical 2. And that is my linear factorization of my function after having divided out 2 sets of imaginary numbers. Okay? This problem is more complicated than some of the other ones. Okay. All right, so I will post Math Excel 2.5 and do that by the due date.